Okay, so this is my capstone project, at least as far as I got before our current situation got a bit out of hand. So what we have here is a steam-powered generator, although today we'll be running it on compressed air. So basic components, we have a weed whacker engine, washing machine motor, welding cart, and a little 12-volt battery here. So the way this works is your standard 2-cycle engine here. You've got a piston that goes up and down. When the piston is at the top of the stroke, there's a magnet on the flywheel, and I've adjusted this so that when the piston's at the top of its stroke, the apex, your reed switch is going to be triggered by this magnet, and that will send current to this solenoid, which will actuate a valve, and that valve will send a burst of our air or steam into the cylinder, causing the piston to go down. All right. Now, the reason this magnet is already on this flywheel is because in normal use you would have a coil pack, like right here, or off of these screws, and when the magnet passes the coil pack, that would generate an electric charge, and that would be the spark for the spark plug. Sorry, the current for the spark plug. But since we're running on air or steam, you don't need any combustion. So we're repurposing this magnet as a signal for our reed switch, which is important. It sets up the engine timing. So off of that, we have this big heavy flywheel, and what that's going to do for us is, as this spins, it's going to pick up momentum, and that momentum is going to carry the engine through the rest of its stroke, mainly when the piston goes down, and then this momentum forces the piston back up, and the cycle repeats again and again and again, and that's your engine spinning up, which is nice. So this whole thing here, from here to here, is a washing machine motor. There's a washing machine bearing right here, and the washing machine axle right there. And the reason I chose a washing machine motor is threefold. One, it's alternating current, and I just wanted to work with alternating current. And two, it's meant for low RPM, and three, it's permanent magnet. So the fact that it is low RPM is very important, because if you use something like a car alternator, which you'll find a lot of people on the internet using a car alternator for a generator, you are required to spin that car alternator at around 1200, 2000 RPM, same as your car would idle. My car idles at 1100 RPM. Anyway, so this is meant for more like washing machine runs at maximum, like top speed, dry cycle, spin cycle is around 200 RPM, so much slower, which is perfect because our steam engine is high torque but very low RPMs. It does not go very fast, but it is very hard to stop. So this washing machine motor is absolutely perfect for this situation, and it would work really well for wind as well when you're dealing with those low RPMs. Now, inside of a washing machine motor, you have permanent magnets on the outside on this wheel, which on the inside of this wheel, but the outside of the stator. The stator stays in position, and that has all your coils on it. Anyway, that's great, because if you used, say, an alternator again, that would a car alternator, because a permanent magnet alternator is its own thing, which is more or less what this is. A car alternator would require a current to generate the magnetic field that would produce power. So you have to have power in order to create power with a car alternator. So this, I don't have to worry about that. The magnets are there. They always have a magnetic field, at least for the next couple thousand years. And now inside here, there's big copper coils. And as our magnet passes over those coils, that's going to generate electricity for us. These coils are wired up. It goes like phase A, phase B, phase C, and then back to phase A. And yeah, so there's 3 phases. They're not connected to each other. So that's generating our 3-phase AC current. Here are 3 phases coming into this big old bridge rectifier, which converts it to DC for us. We're going to need DC to recharge this battery that's firing the solenoid. Now, this is where the stay-at-home order or whatever took effect for me, and I can't really get the components I need. So we get in order to charge this battery, we're going to have to bring this voltage way down, because this generates more voltage than I would have ever expected. We're getting around 100 volts once it's converted to DC, which is way too much to put straight into a 12-volt battery. It goes without saying. The issue is it's also too much for most charge controllers, like a solar charge controller. So I would need a more specialized wind charge controller to make that work. The other option we have, which is in many ways a better option. Sorry, I should elaborate on that. So we would have a charge controller hooked to the battery. So the charge controller takes the DC. The bridge rectifier creates DC. That goes into the charge controller as DC, goes into the battery as DC. Then you run an AC appliance, which is what most things run on, is AC current. You need one of these inverters. This is a little 300-watt one. And the issue with that setup is pretty obvious. You're converting from AC to DC, then back to AC. You're going to lose like 30% of your power doing that. So it's not super efficient. What I should have originally done, knowing that this would produce so much voltage, is on our ACM we're getting around 100 to 140 volts. That will run any standard appliance. So you could draw a load straight off of this AC, one of these phases, and you could even use a standard AC to DC converter to charge the battery if you did that, which is a lot more obtainable in that right voltage range to take from 110 down to 12. But that's all said and done now. So just to showcase some of my workmanship, I grounded the battery to the cart. That way I wouldn't have to run 2 wires for everything. You can see up here, grounded to the cart. This is actually grounded also to the cart. It's welded to the cart. I'm not trained in welding at all. This is one of the $110, $100 Harbor Freight welders, so don't burn me too much on that. And there's a lot of things that I could have ironed out, could have done better. Wish I had, for the fit and finish. I probably wouldn't have just welded a socket attachment to the shaft and then put a Carter pin in it to keep the flywheel from unscrewing. It is still removable though, but it works. But I could have done that better, and I could have given it more of some type of joint that would give it a little bit of play, so my alignment didn't need to be dead on. And then also, one thing I've learned a lot working with like boat trailers is when you're gonna run your positive through your grounded surface, which is this, you don't want to have your grounded surface overly sharp, and like for some of these wire pass-throughs, it's a little sharp. So what you want to do is grommet, put a rubber grommet in there, so you don't wear through and have a short. Anyway, why don't we hook up from there and see what it does. First, good practice. If this was running on steam right now, you would have steam oil mixed into you would get a spurt of steam oil with every spurt of steam. That would keep the engine from rusting, because obviously water in engine is no bueno. But we're just going to put some 3-in-1 right in there. Hook that up. Plumbed it up nice with some tape, so that helped with our efficiency quite a bit. And give her a spin. Wrong way. There we go. What on earth? Alright. We're spinning. Now. Just to show you, we are generating some current here. Sorry. That's 120 volts there, DC. Thank you. See, very low RPM. Could use some dialing in, for sure.